Hello everyone, welcome to Applied Chemistry Tutorials. Today we'll talk about hybridization of organic compounds. Organic compounds are mostly carbon compounds, so we'll start with explanation for carbon tetravalency. Carbon is a group 4 element in periodic table. Its electronic configuration is 1s2, 2s2, 2p2. So it has two unpaired electrons, so it should have valency of 2. During chemical reaction, it absorbs energy and one of the 2s electron of carbon gets promoted to 2pz orbitals. So now the total unpaired electron number is 4. So now it should have valency of 4. But the question is, why equivalent tetravalency? 1 2s and 3 2p orbitals cannot make equivalent tetravalency because 2s orbital is spherical and 2p orbitals are dumbbell shaped and perpendicular to each other. So if they cannot make the bond angles of 109 degree 28 minutes and equivalent tetravalency. This indicates the concept of intermixing of s and p orbitals of carbon atom, that is hybridization. But before going into the hybridization, we'll talk about types of overlapping which happens between the two orbitals of two different atoms. So we'll focus here on the carbon atom. Carbon atoms has s orbitals which is spherical and px, py, pz orbitals which are perpendicular to each other and dumbbell shaped. Now there are two types of bond. The first bond is sigma bond, which is generated by head-on overlapping of the orbitals along the internuclear axis. There are three types of sigma bond. The first one is formed due to SS overlapping. Two spherical s orbitals overlap with each other. SP overlapping due to the overlapping of s and p orbitals, and pp overlapping where two p orbitals oriented in a same internuclear axis, they can overlap to form pp sigma bond. Now the second type of bond is pi bond, which is generated by sidewise overlapping of two parallel p orbital. As you can see here, two py orbitals are sidewise overlapping to create the pi bond. Now let's compare the bond strength. Due to head-on and large extent of overlapping along the internuclear axis, sigma bonds are comparatively stronger. Now bond strength varies with extent of overlapping. Spherical charge clouds of two s orbitals cannot overlap very strongly, as you can see here for the ss overlapping. Directional charge cloud of p orbitals along xyz axis results in higher extent of overlapping, as you can see for the sp overlapping and pp overlapping. So if we compare the bond strength of the sigma bonds, pp overlapping has the strongest bond strength, followed by sp overlapping, and ss overlapping has the least bond strength among the all sigma bonds. Now because of the sidewise and lower extent of overlapping, pi bonds are comparatively weaker than the sigma bonds. Now coming back to the concept of hybridization. Hybridization happens because of the intermixing of the orbitals of a single atom. Now we have seen this energy diagram of carbon atom in ground state already. Here the electronic configuration of carbon atom is 1s2, 2s2 and 2p2. This is the energy axis. Now in activated state, one of the 2s or electron gets promoted to 2pz orbital, makes total unpaired electron 4. In sp3 hybridized state, total sp3, this 1 2s electron and this 3 2p electrons makes up to make 4 sp3 hybrid orbitals. Now point to note that for hybridization, the orbitals should be of only slightly different in energy. As you can see for the 2s and 2p, those are slightly different energy. And number of orbitals undergo hybridization generate equal number of hybridized orbital. As you can see here, 1 2s, 3 2p, total 4, that makes 4 sp3 hybrid orbitals, and they are of equivalent shape and energy. Now let's dig deep little bit more on sp3 hybridization. So for the sp3, 1 2s and 3 2p take part and form 4 equivalent sp3 hybrid orbital which are oriented towards the 4 corners of a regular tetrahedron, making the bond angles 109 degree 28 minutes. Each sp3 orbital has 25% of the s character and 75% of the p character. In methane, half-filled 1s orbitals of 4 hydrogen atom overlap with 4 sp3 orbitals of this carbon atom and form 4 sigma bonds. Now coming to the sp2 hybridization, as the name suggests, 1s, 2 p orbitals, here px and py, they intermix to create 3 equivalent sp2 hybridized orbitals. These sp2 orbitals are oriented in a trigonal planar arrangements with bond angle of 120 degree. Now each sp2 orbital has 33.3% s character and 66.7% p character. Now here is the energy diagram for the sp2, 1s, 2p, they got intermixed. So one of the p, that is pz, that remain unhybridized. So that is now perpendicular to the sp2 structural plane. Now let's see how the sp2 hybridized carbon atoms are attached in ethylene. Now in ethylene there are 2 carbon atoms, both are sp2 hybridized. One or sp2 orbital from each carbon atom overlap with each other and make the sigma bond. The other 2 from each carbon atom, they overlap with hydrogen 1s orbital and create another 4 sigma bonds in the ethylene. So total 5 sigma bonds are formed in ethylene. Now the unpaired the unhybridized pz orbitals are perpendicular to the sp2 structural plane, but they are now parallel to each other for 2 carbons, so they can sidewise overlap and create the pi bonds. In the picture they are quite far apart for the clarity of the picture, but in real scenario they are quite close, so they can sidewise overlap. You can see in this picture very clearly there are like 5 sigma bonds and 1 pi bond is formed. Now C double bond C is formed and free rotation around C double bond C is prohibited, so it has a planar structure. Now coming to the sp hybridization, as the name suggests, 1s and 1p, preferably pz, these 2 orbital intermix with each other to create sp hybrid orbitals. 2 sp hybrid orbitals, these small lobes are represented and this should be omitted in real scenario. Shortly we will discuss why. So 2s and 2pz, preferably orbitals carbon atom intermix to generate 2 equivalent sp hybridized orbitals. sp orbitals are oriented in a linear arrangement with bond angles of 180 degree, which is known as diagonal hybridization. Each sp orbital has 50% of s character and 50% of p character. Now let's see the energy diagram. 1s, 1p intermixed and 2p, here px and py remain unhybridized. So they are now perpendicular to the sp hybridized orbitals, here represented by purple color. Now let's see how the sp hybridized carbon atoms are attached in acetylene. So there are 2 carbon atoms in acetylene. One of the sp hybrid orbital from each carbon, they overlap with each other and form sigma bond. The other sp hybridized orbital overlap with hydrogen 1s orbital and create another sigma bond. So total 3 sigma bonds are formed. Now unhybridized px orbitals and py orbitals, they sidewise overlap and create 2 pi bonds. You can see in this simple structure there are total 3 sigma bonds and 2 pi bonds are formed. So there is a triple bonded structure. So HCCH, this is a linear structure which is formed in acetylene. A little note here, p orbitals have plus and minus 2 wave functions represented by 2 symmetric lobes. During hybridization, positive p lobe adds to the s orbital, creating one big lobe, whereas the negative p lobe subtracts from the s orbital and creates one small lobe. So this is one sp orbital is formed which is asymmetric, and during sp hybridization two orbitals are formed. So total sp hybridization looks like this. So are the sp3 and sp2, where in sp3 there are like 4 big lobes and 4 small lobes. Similarly for sp2 there are 3 big lobes and 3 small lobes. Now these small lobes are usually omitted for clarity. As you can see, for the sp2 the small lobes are omitted and only the big lobes are represented, which you have already seen previously in this video. Now coming to the effect of hybridization on bond length, we discussed little bit about this in our previous video. You can go and check those. We'll discuss the reason behind this. So in ethane, ethylene and acetylene, all of these three compounds have 2 carbon atoms. In ethane, carbons are sp3 hybridized, ethylene sp2 and acetylene sp. Now if we compare the S character, in ethane sp3 that is 25%, in ethylene sp2 that is 33.3%, acetylene that is S character is 50%. Now it is well known that S orbitals are closer to nucleus compared to the p orbitals. Therefore, higher the S character leads to higher electronegativity and hence smaller size of the hybridized orbital. The smaller size of the hybridized orbital has effect on the bond length. As you can see for the CH bond length, as we go from ethane to ethylene to acetylene, S character increases, so the electronegativity increases, hybridized orbital size decreases, so the bond length also decreases. And the effect is more pronounced for the CC bond length. As we are moving from ethane to ethylene to acetylene, the CC bond length decreased a lot. So that's all for today's talk. Stay tuned with us for the next video. Thank you.